Good day. For those of you who don't know me, my name is Douglas Harder, and in this topic, we're going to discuss linear combinations of vectors. So in this topic, we will discuss linear combinations of vectors. We will look at an example. We will discuss some questions we may ask about linear combinations. And then we will look at a few special cases, such as the average of vectors and weighted averages. Now, given a vector space over a field F, and given m vectors all in that vector space, together with m scalars all in F, we will call the sum of products alpha 1 times v1 plus alpha 2 times v2 plus going all the way up to alpha m times vn m, a linear combination of these m vectors and corresponding scalars. We may also write this using summation notation. So here we see we are taking the sum k going from 1 to m of alpha k times vk. Here is an example of a linear combination of 5 vectors in r to the 4. And when you calculate this linear combination, you get the vector at the right-hand side. Now, one important point is that a linear combination is always made up of finitely many vectors. We cannot take a linear combination of infinitely many vectors, as the sum of such vectors may simply not exist. For example, if you were to just add the two-dimensional vector 1, 1 to itself an infinitely many number of times, well, that adds up to the vector containing the entries infinity and infinity, which is not real. So such a sum is not a real two-dimensional vector. Also, in general, we will assume that none of the vectors in a linear combination will be the zero vector. For if this linear combination did in fact equal the target vector u, then we could actually add any scalar multiple of the zero vector onto this, and we will still get the vector u. So the zero vector cannot contribute to a linear combination, and thus in general we will assume that none of the vectors that we are taking a linear combination of are the zero vector. Now, one of the most significant questions we will ask in this course and try to find an answer for is, given a target vector u in a particular vector space and given m vectors v1 through vm also all in that same vector space, do there exist m scalars alpha 1 through alpha m all in the field F such that u is this linear combination of the vectors v1 through vm? That's actually a very difficult question and a significant component of this course. Using the terminology of linear combinations, we may say, given a target vector u and m vectors v1 through vm, all in the same vector space, is there a linear combination of these vectors v1 through vm that equals the target vector u? Now, another question we may ask is, given m vectors v1 through vm all in a given vector space, what are some of the properties of all possible linear combinations of these m vectors? Now, if m is equal to 1, then we are considering all linear combinations of a single vector v1. That is, we are simply considering all scalar multiples of a single vector. Consequently, in this case, a target vector u is equal to a scalar multiple of v1 if and only if that is explicitly true. So u must be, for this to be true, there must be an alpha such that u is equal to alpha 1 times v1, in which case u lies on the line starting at the origin and going through the vector v1. Also, all possible scalar multiples alpha 1 v1 of this one vector forms a single line in the given vector space. Now, given m vectors v1 through vm all in a given vector space, if all of the alpha sub k's are the same value, specifically 1 over m, then this specific linear combination of these vectors is simply the average of these m vectors. Given those same m vectors, if the sum of the scalar multiples alpha 1 through alpha m is equal to 1, then the linear combination of these vectors and corresponding scalars is said to be a weighted average of these m vectors. So, following this topic, you now have a deeper understanding of the concept of taking linear combinations of a set of vectors. You are aware of some of the questions that we will be asking throughout this course, and you understand the idea of averages and weighted averages of vectors. Here's the references, acknowledgements, the colophon, and a disclaimer. Cheers!